think we're live. Today we'll do a couple of things. One of them, we will go back to TinkerCad a little bit just to show some of the things that we're doing there, different workflows. It really is TinkerCAD. You know, it's not something that you're going to use to replace SolidWorks or Fusion 360 or one of those type programs, but it's really easy to put something together really quickly and get an idea out there. And print it or whatever. You don't have to print the parts. There are other things that you might want to do. We're just looking at printing in this course. We're going to also talk about designing for FDM. So designing for this kind of printing, there are some things that you might want to think about. A lot of times when you're printing something here or you're designing a part, you're not necessarily designing for FDM. You're just designing a part and you want to test out that part by printing it. So that's a little bit different thing. There are some things to think about even then though. So we'll talk through some of that stuff. I've got a couple of things to show over here, and why don't we start? Let's start with some of the stuff I've been doing. So let's back up a little bit, get that off the screen. Here's the violin. So I've put some fasteners in it, put a few pieces together. Still have another piece to print. Actually, there's two other pieces to print to it. We did have a part failure in the print. I saved it. Well, I say I saved it. I don't know that I've saved it yet, but I glued it back together. So this piece right here, it starts here and it actually ends here. So all of that is printed as one piece. The problem with this comes from the way I printed it. So I printed it standing on this end, so it was standing upright like this, just this section of it. And on some printers that would have been no big deal, but on these printers, the ones I printed on, the bed that it's standing on moves back and forth, you know, to create the y-axis. Other printers, all of that motion X and Y is handled by moving the print head back and forth, and the bed just drops down to create the z-axis. So that's a different mechanism altogether. But when you put a really tall, relatively heavy, these aren't light, they have 4 walls and relatively high, I think it's only 20%, but they end up relatively heavy. When you print that standing on its end, then what happens is as this bed moves back and forth, that column gets taller and taller. And it starts shaking a little bit at the top, and eventually you'll get the nozzle catch on something that it printed. So here it actually caught on, it's buried inside here right now, but there's one of these slots where you put a nut. I'll show you that later on today. Where you put a nut in here to bolt things together with, and it caught on the edge of making the roof of one of these things, and it was just enough to break the whole thing off, and it just landed on the bed and sat there while the extruder tried to print the rest of the stuff just in midair, so it didn't work. So what I did to fix that is, well, we'll see if it fixes it. I don't know if I may have to reprint the whole part, but there are screws that hold it together this way, and it's screwed down to this bottom plate, so maybe it's going to be good enough to withstand whatever tension. Well, it's going to be in compression when we put the strings on it. The strings are going to try to pull everything together. So I'm actually more worried about bending on the back side, like it wants to collapse up, but we'll see. Anyway, what I did is I reprinted just this top part, the part that didn't print or that tried to print in midair. The whole thing was a 12-hour print, so I didn't want to start it all over again. And then I glued it back together. You can see the seam right there. I didn't try to hide the seam just because I don't know that it's going to work. If it does work, then I'll come back and try to sand this out and smooth it up a little bit. But how you can do this, I think I already kind of showed it, but in Prusa Slicer, you can actually split a part into two or multiple pieces. In this case, I was just splitting it into the part I'd already printed and the part I hadn't printed. So what I did is I resliced the part, and then in this case, I had a really good marker because it failed right at the top of one of these little holes where the captured nuts go. And so I could find that layer in the slice, and then it gives me a layer number 798 or whatever it was. And I just sliced the part at that layer and was left with this little piece and the piece I'd already printed. And I just threw away that part and printed this part and then glued them together. Cura, you can do a similar thing, but you do it a little bit differently. It doesn't necessarily have a split command. At least I don't remember a split command in Cura. But in Cura, you can just put parts a distance beneath the build plate, and they'll only print what's above the build plate. So in that case, you could slide the part down in the Z direction until the layer that you were interested in was right on the surface of the build plate, and print that, and it would just print the top part, whatever's above the build plate. So don't think they're always complete failures if you have to fix them later. Now I just use super glue here, which is probably not the best thing. If I really intend to keep it this way, I probably should have used a slow drying resin, like a epoxy, something that takes, not one of the fast cure, not one of the 5-minute cure things. In general, the faster something cures when it dries, the less it's going to have as far as long-term strength if you really needed to do a lot of work. And so one of the slower drying epoxy resin glue type things would be a better approach here. But I just used super glue and an activator, and I clamped it tight, and I'm relying a lot on the fact that there's actually screws. I don't know if you can even see them, but there's one of them. I haven't screwed it in there, but there's 2 screws that actually clamp these pieces together even when they're not broken, and then there's 2 here that clamp it this way. So I think there'll be enough, and the strings will pull everything together too. So all of that to say, don't think that every print failure is a absolute failure. You might be able to save them. We'll see. On the other side of things here, if you're thinking of printing something like this because it's going to save money, that's probably not true. I went and found a Amazon electric violin, and probably the amount of hardware you got to have, tuning pegs and strings and all these little nuts and bolts, and this is an electric one, so there has to be a piezo pickup and a preamp and all this. By the time you get all that stuff, it's about the same amount of money as just buying the cheap one off of Amazon. Now, is this one going to be any better than the cheap one? I have no idea. I don't know. But it'll be interesting because it's 3D printed, so it's kind of interesting to do it that way just to see if it works. But as far as saving money, unless you could make this equal to one of the multi-$1,000 violins, you're not really saving any money by printing it yourself. It's more of a exercise in just doing the print and assembling it and seeing if it works. It's a little heavy feeling to me. Violins are typically pretty light, and it already feels a little bit heavy, and there's still more of it to go. We'll see how that ends up as far as playability, but a lot of that depends on who's playing it, I suppose. I'm not a violin player, so we'll see. My son, it's a little big for him. He's only 8, so I don't know if he'll be able to play it or not. He could play it, but we'll see. Anyway, just wanted to show you that. Here's another thing I printed. This is a swappable carriage, so it's going to mount, well, I'll have to take this part off and it'll mount in that place, and this is the plate that puts the hot end and the fan shroud and all that on here, and then what I can do with that is it'll mount there, and there's a little lever here. I need to show you something about this one because it's not quite right yet, but this little lever cams over and locks it in place, and then you can print, or you can switch other things out here. So I'm going to put one of these plates with the the right shape in here, but it'll mount a pin so that you can have a plotter, and another one where it can mount a little tiny DC motor for very light CNC milling type stuff. These, I'll show you where I got this one. This one is from Thingiverse is where I got it, but you can get it other places. This is it right here from Proper Printing. He has a YouTube channel where he does all kinds of stuff. He made a Ender 3, but it's foldable, so it folds down into a little briefcase looking thing. And he's got a lot of different interesting things, but this is where the design came from. I have one on another printer, and they work surprisingly well. Even PLA, you'd think that PLA being that close to the hot end would not survive, but it's actually not close to the hot part of the hot end, so it actually works okay. But he's got several different pieces. There's the main plate. There it is with a Dremel-like tool on it. Just different prints of it. There's some. He's got a laser mount. Oh, I have one of these lasers. I might could mount a little laser on there too. Didn't really think about that. But there it is in place back there in the back, the white piece. So it does create a little bit of a different, it's going to offset this thing a little bit. So I have to reset where the y-axis home's at. But that's just a matter of moving the little limit switch back here to reset where 0 is on the Y corner. What I was going to show you about this lever is that it doesn't work quite correctly, and it's because of the way I printed it. So the idea would be that, well, it would go this way. It would cam over, and I don't want to do it right now because I don't have the screw in here to actually help out holding this thing, and so I'm pretty sure it would just shear this little stem off of here if I cammed it over. But what the problem is, and I don't know if you'll even be able to see. Let's see if we can get it to focus on this part. Maybe it's going to focus on everything but that part because it's so tiny. But it was printed on the bed this way, and right at the bottom here, you can see that it's a little bit thicker here than where the main part of this cam exists. That's usually called elephant's foot, where the bottom of a print is a little bit wider than it should be. And what happens there is when you're printing that first few layers, you're printing usually slower, maybe even hotter. Your layer cooling fan for PLA is not on, so you're trying to get it to stick to the bed. So it's a little bit gooier when you're printing, and because you do want it to stick to the bed. And what that does is that makes those first few layers a little bit wider than what you intended for them to do. So a couple of things that you can do to counteract that, if you made the part, or if you have a way to edit the part file itself, you can put a little chamfer here so that the first few layers are actually smaller than you intend, and anticipate that, well, they're going to end up bigger than what I have in the model file, and deal with it that way. So if you can modify the part file, you can put a chamfer all around the bottom, so it's like a little angle that makes it come indent some, and you can deal with it that way. I don't know if he's released the files to modify these things. No, he does have one file that you can modify. You can modify STL files, but it's not as easy to do things because it's an STL file is all the geometry just described in triangles. So it's not like a SolidWorks file where you have all of this information about this was created by an extrude, or this was an actual arc, or it doesn't have that information anymore. It's just triangles that make up the outer surface. So they're a little bit harder to modify. Another thing you can do is in the slicer itself. So there's a thing called horizontal expansion. And so you can, if the holes are coming out too small or too big or whatever, you can modify this horizontal expansion to make holes larger or smaller is usually what you're doing with that. But there's also a horizontal expansion for the first layer. So you can take and just shrink down that first layer by 1% or however much you think you need to shrink it down by. I think that's what I'm going to try when I reprint this, in order to get that elephant's foot gone. Of course, you could just go in there and try to file it down, sand it down to where it fits. I might try that too. Another thing I could do is I could just try printing it this way, where the elephant's foot is on this surface, which would be much easier for me to file if it gets in the way. I actually don't think it would get in the way. But those are things that you have to take into account when you're printing something that when it becomes a real thing, it exists in the world, the way you created it might affect how it actually works. In this case, it makes it not work. What else do I want to show? Oh, we went through a few days ago the teaching tech sequence of things to do for calibrating your printer, and one of them's a retraction test. I don't think we actually printed it on the stream because it takes 30 or so minutes, 40 minutes maybe to print. I printed some off the thing, and they don't show any retraction issues at all. So it's not because the printer is that well tuned. These are meant to go down. Well, this one goes down from 5 millimeters of retraction to 7.5. So that is kind of where this printer works best at. This one goes down to 3.5 to 5 something, 6 something. I don't remember. And it doesn't show any retraction. I actually intentionally went and got this filament thinking that it's an older filament that, you know, would be more likely to string, but it didn't show any. I think the reason is these larger columns like this, they have room to wipe the filament clean inside the, you know, the infill, so that when you move over, you don't get all that stringing. I did print the one that I showed you in class. This one is a much harder file to actually not string, because as it gets closer to the top, so this is with, whoops, it's very small. This is with 3.5 millimeters of retraction at 45 meters per second, or millimeters per second, not meters per second. Good grief. And so you can see this one is printed about the same, actually faster retraction speed as this bottom layer here that shows no issues. But here you can clearly see that, well, no, it could be better. So I do like this one a little more. For one thing, it's way faster, but it only does one thing at a time. You know, you have to change one variable, print one of these, takes about 10 minutes to print it, then change it again. And in this one, you can see that there's a lot of issues here. Now, these aren't that bad. They look bad, but they're actually pretty easy to clean up, just with a hobby knife and a heat gun. So you can, if all you have are these little wispy ones, like maybe this side here where it's real thin, a lot of times you can just hit that with a heat gun or a hair dryer, and they'll just kind of resorb into the post that they're from. But I kind of think I like this one more. Somebody in the comments said they had the same issue with these, just don't show any retraction problems at all. Now, if you're printing something that doesn't have these tiny little peaks, then okay, yeah, no sense in worrying about it. If all you're printing is bigger areas like this where it's not gonna have I did go in the G code itself to see if the retraction was changing, and it does show in the G code that for these files, it does show a change in the retraction in the code itself, but the results don't show any difference at all. This one, these I can clearly see a change when I modify a variable. So I kind of still like these, even though they only have one thing at a time that you can test really. But I don't know, I still kind of like these so far. Maybe I'll find a reason that I'll like these, but right now I still like these. As far as when you're doing this for an assignment, it doesn't matter what you do. Just do something, print one, make a change, print another one, and report that, hey, I changed this and this happened. So it doesn't matter which one you use, although I do kind of like the smaller one for actually visually seeing that something's changing. What else? Oh, all right. I was going to, now a lot of your printers, if you have the Pros or the version 2s, they have a little piece of hardware here that lets you tension this belt easier. So the way that this printer tensions this belt is you loosen these and you pry this over and tighten them back down. And there can even be a similar thing on this axis also, where you loosen these and pull it out, and that's how you tighten the belt. Now this belt's actually pretty tight. But when I ordered this sheet, the PEI bed sheet here, right there, when I ordered that, I also ordered a little end here that is adjustable. So these came from Sainsmart. No particular reason I ordered from there, except I was already ordering other things from there. So they do have accessories, and let's see if I can find them in here. I've ordered some of these other things too that we'll look at in the future. It looks like they have their own version of the filament drying box. Oh, I will mention something about this one. This box. It does seem to work. I did try to get a bad roll of filament so that I could dry it out and see if it worked. The way it works is basically there's a heater in here that it acts like a really low temp oven to evaporate out the moisture, which is the same thing that you do a lot of times like in a food dehydrator or in a toaster or something like that. They've just built it into this. The issue I had with it is I did have an old roll of filament, but it's an old roll that I don't even know if they make this style spool anymore, but it's a really wide spool. So it's not this spool, but it's really wide, and it doesn't fit in the little cavity here. So that's the only issue I've had with this particular thing, is that I do have some spools of filament that don't fit in there. I don't even know if they really make that form factor anymore, but if for some reason you're using a spool of filament that's excessively wide here, it's not going to fit in the box to even begin to dry. It says basically you turn it on. I don't think it's plugged in. Yeah, it's not plugged in right now. You turn it on. It doesn't have an actual on-off switch. It's just plug it in or unplug it. So I bought one of these. Where you can just have a switch for anything. So I bought one of these to have an on-off switch for it. You turn it on, set the temperature, maybe 50 degrees Celsius or whatever, pretty low. Obviously, if you put it too high, then you're going to start melting the filament or melting the spool that the filament is on and have all kinds of problems. So it's pretty low temperature, and it heats it up for 6 hours is the default. You can change the amount of time that it heats, but 6 hours. So it does work. Doesn't work with every roll if it's really wide. I don't think that many rolls are that wide anymore, but it does work. I just couldn't get the roll that I wanted to actually test that was printing badly. I couldn't get it in there, so I'll have to see if I can find another roll that doesn't print too well to see if it will make a difference in the printability of a roll of filament. Or maybe I can unspool some of the stuff off of the roll that I know is bad and put it on something else that will fit in there. I don't know. Anyway, all of that to say that apparently Sainsmart has their version of this same thing. So it looks very similar. It's got 4 buttons instead of 2. I don't know. It's actually on sale right now. Got one of these that will, actually not one of those, one of these that we'll show later. But here's the little device. $13 for the X-axis belt tensioner. The PEI sheet, yeah, there's the PEI sheet that I put on there. A little bit high, $26. It does come with the magnet that holds it down. In this case, for our printer here, there's already a magnet under it, so I didn't have to apply that. Anyway, this thing, I wanted to show you, if you have a printer that doesn't have this, for $13, you can mount this little guy on here. And it does come with hardware, although I don't know that you would need, there's hardware here, so I don't know if you would need to change out the hardware or not. It actually looks like you could just use what was already there. If you don't want to buy anything and you have filament, you can print these. For most printers that have this size, the 20 by 20 extruded aluminum, they on Thingiverse have printable versions of this, screw and everything. You just use the old hardware that was on the old piece, put it on the printed version, and then you have a little knob here that you can use to tension the belt. For both axes, they have those that you can get for most printers. I haven't actually printed one of those, but you could do that. So what you would do, hopefully it's not too terribly difficult. So we loosen it up. Got to get the belt off of here. I do remember it being a a little bit tricky to do to get this belt on here, but there we go. Now, this one, the belt could just come around here. This one, I actually have to feed the belt in here. Also, this one has a grooved pulley versus this one just had two bearings back to back. So I don't know if that will actually help us keep the belt. We didn't really have slipping problems on this to begin with, but now we certainly won't, at least not there. So let's see if we can get this. Okay, it's going to mount that way. Okay. Let's see, what hardware do we want to use? I'd rather just use the hardware that came on it, but it is a little bit thicker plate, so I'm going to use the hardware that came with the little part, the belt tensioner. This is always a tricky part, getting these. There's probably, it might be simpler to do this. Put them on and then slide them in there. And keep forgetting that I don't know where the camera's looking all the time. So there's that. Where'd my other one go? This. There. Get those to slide in the little slot there. Make sure our belt is not out of its spot. Now the problem is I can't see what I'm doing back here. You have to. There it is. All right, so we got that back in. Now let's mount this guy. Now these little inserts, you can tighten them up and they don't actually catch. So you do have to be careful that they catch in the groove there and they don't end up tightened where they will just slide out. So I generally try to spin it pretty fast to get them to swing up there in place, which they did. So far this has been a pretty easy, ooh, look at that. Don't need to get that out of whack. All right, and then we can just tighten the belt by turning this knob here until it's the tension we want. If this belt is loose, then what will happen is in your prints you'll have blobs when it's in the slack position. You know, it won't move, and so it'll think it's moving. Again, these printers, none of these printers have any real feedback on them. They do have a couple of stepper motors out there that, or a couple of accessories that you can add to a stepper to count its steps. Did it actually take the steps you told it to take? I tried to buy one, but you have to have a particular motherboard so that you can plug these things into, and I don't have one of those motherboards right now. So if I get a motherboard that has socketed drivers, I'll put one of those on one of the printers so that you can see what it does. But in general, these printers do not know where the print head actually is. They know temporarily, so they home, right? They home, and then home the Z-axis, and they know where they started. So they know they started in this corner, and then everything else in the entire print is based on, well, I knew where I was back 300 lines ago or 10,000 lines ago of G-code. I knew where I was, and I assume all the movements I've made actually happened, and I know where I'm at. But if anything ever happens where you tell it to make a move and it doesn't actually make that move, that whole dead reckoning approach falls apart. So you don't want to skip steps. You don't want slack in these belts, because all of that will create problems later on in your print. Looks like we're back, and this is really simple to use. You can probably over tighten these now because it's so simple to do, but in general you don't want these to flop around. You want them to be very resilient. You push them and they come right back. You don't want any flopping at all. So that's actually a really simple upgrade if you don't have one of these already, and it's not terribly expensive, and you can print them yourself. So on Thingiverse Let's see if we can find one real quick. Belt tensioner. Thingiverse is always kind of slow, so it'll eventually catch up, I think. Yeah, here's one for the Ender 3 belt tensioner. That one you can kind of see. I think it might have both of them in here. This is for the y-axis though. Wow. Well, you get the idea. I don't know if I want to wait for this thing to load. Like I said, Thingiverse can be really slow, but here's several different designs. This one I've seen before, and it seems like a really good one. It's pretty simple also. But they do the same thing. This is really simple right here. If you don't have a way to tension the belt that you have, you don't have one of the little, you don't have one of these. You've tried pulling this out and you just can't do it, and you need something quick. This thing, it just goes and it clips on the belt. So if you have a spot in the belt where it's, maybe on the bottom down here or somewhere where it's not going to go around a pulley, then this little S shape will add just a little bit of tension to the belt. Some of your printers actually ship with these. They look like the middle part of a clothespin that's spread out. And so you might see these as a really easy way. It's an easy print, easy way to quickly add belt tension if you just can't get the belt tight enough by pulling on things and tightening stuff. This is a way that you can just clip it onto the belt and it will tension up the belt. I don't know if I would want them as a permanent solution, but they will help you along for a while. All right. What else do we need to do? I think we've looked at all of the things I've got over here. Let's talk a little bit about designing for FDM printing. So remember, a lot of times what you're really doing is you're designing something for it's going to be CNC or injection molded or whatever, and you just want to print the part to test if it's kind of right. That's not what we're going to talk about. We're going to talk about actually designing for something that you do want to print. Like the end goal is to print this thing. But if you are designing for prototyping or you're prototyping, you want to print this thing out to see if it fits, don't go back and redesign your model just because your print didn't fit. Make sure that your print actually turned out the way you designed it, because just like we looked at with our little piece here, it's designed maybe correctly, but I printed it and the act of printing it created this problem. So don't just automatically assume that if you print something that you design and it doesn't fit, then don't assume that you need to go redesign it. First, check to make sure did it print the way I intended it to or not. And then figure out that, okay, yeah, the printing is fine. I really did make this tolerance wrong in the design file. So first, that's a different thing altogether. But here, let's talk about actually, I want to print this part. That's the end goal. So a lot of times with these particular printers, you're not trying to print something that's an end-use product unless it's a artistic type thing. A lot of these printers are going to have trouble printing not reusable, but parts that get heavy use. That is one reason to print in different materials, though. Maybe the PETG, which is a more usable material than the PLA. PLA has some major drawbacks. One of them, the major one, being that it's really sensitive to temperature. You print it at 200 degrees Celsius or somewhere around there, so that seems really high, but PLA softens way lower than that, like, I don't know, 70 degrees Celsius. So now you're getting into the range of temperatures that in a hot day inside a car or something like that, that might be enough to soften it up. It won't like melt it, but it'll be enough to soften where it deforms. PLA is also really hard to finish if you're trying to sand a thing or do anything like that with it. It's hard to do just because it's it doesn't sand well, and if you use a tool like an electric tool of some sort, of Dremel, then you can actually melt it, because the speeds that you're sanding at or grinding at are going to generate enough friction to heat it up beyond its glass transition temperature, and it's going to get soft and melt and make a big mess. So PLA is a good part material to test things out with, or to make things that are going to stay indoors. They're not going to be out exposed to temperature, or you don't have to do a whole lot of sanding to make them look nice. It's good for that. But there are other materials that these printers can print that are going to be better if you're designing this thing for a function. And one of those materials is PETG, the green stuff, or it's not all green. I have a roll of green stuff that we're printing the Violin from. It's a good in between for, you don't really need a printer that's enclosed. Some of these materials that are better functionally than PLA, they have to be printed in an enclosed chamber. PETG does not need to be. It is a little bit tricky to get started with, to get your printer dialed in on the right speeds to print it at, and the right temperatures to print it at, and all of that. But if you're trying to get a part that you want to actually function, and it's going to have to handle some kind of force and maybe a little bit of temperature, then it's probably the best material for these style printers. There are a whole array of materials that you can choose from, like hundreds of materials you can choose from. It's probably the best all-around material for a functional part that these printers can do without changing a bunch of stuff. ABS is another material. In the early days of this kind of 3D printing, which wasn't that long ago, right? The early days of home level printing was maybe 10 years ago, maybe not even that long ago. But in that range anyway, ABS was the material you printed with, and it was just was the thing that was available. Actually, the very first printers that were home kind of grown printers, you used weed eater line. So the same thing that you would put in your weed eater, you would print with that. In fact, you if you've ever wondered, well, why is the filament 1.75 millimeters in diameter? That's one of the big reasons why, is because that was a common size for weed eater line. All right, that doesn't matter at all. But anyway, ABS, it has some good properties in that it is a more tough material. It's not as brittle, not necessarily as strong as PLA, but it's overall it's tough. So if you look at the area under its stress strain curve, there's more area there. It's tougher. It is really easy to sand. It's sand. You can actually polish it, so you can make it really shiny just by sanding it. You can vapor smooth it, so you can use acetone vapor, and it will, if the mist is fine enough, you don't just necessarily pour it on there, but a fine mist of acetone, which is very explosive, so don't do that unless you know what you're doing. It will smooth out the surface so where you don't even see the layer lines. This is all for ABS. But the downsides are that it's tough to print in this kind of printer because it generally needs to be enclosed. It smells bad. It's kind of noxious when you're printing it. It does print a little bit hotter, but about the same temperature that PETG, maybe a tiny bit hotter than PETG. It does want to warp a lot as you're printing it. The part wants to warp and delaminate, and so it's a lot of issues to get it to print on this style printer. Normally, it's an enclosed printer that's got a chamber that's heated, and the whole, it's a different setup altogether. Also, it's enclosed, so you don't have to smell the ABS printing. Other things you think about with some of these materials are very abrasive. So I haven't put it on here yet, but I bought also from, I guess this came from Sainsmart. Yeah. Here are some hardened steel nozzles. So I haven't opened this up yet. Maybe I can get it open and show you what this means. So these little guys. So these are hardened steel nozzle replacement. So it's just the nozzle. The nozzle that's on your printer by default down here is brass, and that's fine for PLA, ABS, even PETG is fine for all of those. But if you start doing any like glow in the dark or wood feel or copper feel or any of these materials that have another thing inside them, it's going to be abrasive. Even glow in the dark is abrasive to the brass nozzle, and it will not very long, maybe half a roll of printing for some of these materials. So some of these materials, even less than that, you can't even do it any amount of time before it's worn a hole larger than the nozzle started with. So you have to switch out for something like this, which is a hardened steel. If you're doing a lot of abrasive printing, they even make these nozzles that have a ruby nozzle on them. So it's, I don't know if it's steel or brass, but the actual core of it is ruby. So that's if you're very serious about printing abrasive materials. I don't have one of those. These are, a few dollars for a nozzle. The ruby ones are like $80 or $90 for one nozzle. And I don't print anything that needs that kind of nozzle. Some materials they need to be really hot. So nylons and polycarbonates and PEEK and all these materials that you may want their properties, these printers by default aren't going to print in that, just because the hot end can't reach the temperatures that it needs to reach in order to print them. All right, so you pick your material. So I'm going to say that if you're trying to build a functional part, the most accessible material for an Ender 3 style printer is going to be PETG. There is a material called ASA that is also in that range. I don't really print with it that much, so I can't talk about it that much. But ASA, I don't remember what it stands for. That material is also kind of in that in between PLA and ABS, and it can print on an Ender 3. I'm not sure if it needs to be enclosed or not, though. That's why I don't really mention it that much, other than it's another one that might be a good functional material. So why would you maybe print something with your end goal being this kind of process? Maybe you're just printing a few of them. Maybe it is more an artistic decorative piece. You can go to Etsy at any day and find hundreds of vases and all sorts of things like that are just printed in PLA or maybe PETG, because it makes a nice vase material because it's kind of translucent. That's the goal. It's not meant to be really functional, more it's just the aesthetic design. Maybe you want to, like we mentioned earlier, you're just testing something out, and we talked about how to go about. Don't necessarily assume that if the printed part doesn't do what you designed, that the design is wrong. First, make sure the printed part was printed correctly. Another thing that you use in parts here are like one-time use or a few-time use type things, where it's a jig. So you've got a machining process, and you've got to hold your block of aluminum at a certain angle to machine it. Or you've already done some of the machining and you got to flip it over and it's got this weird shape you got to hold. 3D printed jigs are really useful because you can print it to hold this oddball shape on your mill or your lathe or whatever. Well, maybe not the lathe, but on the mill. And that's a good use for 3D printing, is printing jigs. Maybe you only use it one time or very seldomly. More and more, they are getting to where FDM and 3D printing in general, so additive manufacturing, is a thing. It's usually on machines that are different from the Ender 3, though, right? It's usually a machine that can print some of the carbon fiber infused nylon materials, so they're actually almost as strong as a straight carbon fiber part or something like that. But those machines are, $20,000 versus your $150 Ender 3. You can eventually upgrade enough parts on here to at least print some material, nylon with carbon fiber in it. You can put the hardened nozzle, all metal hot end. You can build an enclosure. In fact, on this Sainsmart site, I saw one. Let's see. I thought I saw one. Yeah. Here's a really easy way to get an enclosure. It's just a bag you put the printer in. You don't build anything. It's just got a door. I wish I could hover over it. I guess I have to view more. Anyway, it's just a fabric type bag that you put the entire printer in. Have some filament on the back, tools, stuff like that. So if you really want an enclosure, you don't want to build something, that's an easy way to do it. But anyway, you can do all that kind of stuff to maybe get to where you could print some of those more engineering materials. Molds, you might want to print a mold that you're going to cast a material in. A lot of times, most materials like the PLA is not going to survive most molding processes. Most molding processes involve a lot of heat, right? Whether it's you're mixing two chemicals together and they react to harden, that reaction is exothermic, and a lot of the temperatures can exceed the melting or the glass transition temperature of PLA. So molds out of PETG or something like that might be usable. You can't really, there are some printers, again, that can print nylons and higher temperature materials where you could create a injection mold type mold for that process. Those, even the ones that you do find are, they're not long-term use. You're just wanting to get the features down before you make the stainless steel mold or whatever. You can do some low temperature. In fact, later on in the course, I'll do some, I'll use the printed part as the form to create a sand mold, and we'll do some low temperature casting. It's really easy to do with low temperature stuff. Obviously, I can't sit here and do any high temperature casting. There is a process, you might have heard of lost wax casting, where you make a part in wax and then you put investment, which is like a plaster all around it, and then you burn out the wax, and now you're left with a cavity in that plaster, the shape of the wax, and you pour aluminum into it. There's a similar process for lost PLA. Actually, there's even a wax filament that you can do. I haven't done this before, so I don't know how well it works, but there is a, I think Machinable Wax is the company, and they sell a wax filament that you can print a part for lost wax casting. Again, I haven't tried it. Vacuum forming, where you take a sheet of plastic, heat it up, and suck it down over the top of a form. You might get away with, well, with PETG, you probably could. ABS, you probably could. PLA is probably going to be too low. Again, you have to heat that sheet of plastic up for vacuum forming. And so you probably, it's going to be hot enough that it will deform most PLA bucks, the form that you want to shape around. But some of the other, like even PETG, is probably okay for vacuum forming. Vacuum forming, actually, it doesn't look, I don't know if you've ever seen it or not, but it doesn't look like that much is going on, but there's a lot of heat and negative pressure. So you're pulling a vacuum between the sheet and the form, so it's sucking down to all the shapes there, and so there's a lot of pressure that gets applied to that form. But you can do that. You can print a buck for vacuum forming. Obviously, some things to do before you get into printing. You know, you want to design a part for printing, then you need to go and think about your printer being calibrated. We've actually gone through that already, so I don't know that we need to think about that too much or talk about that too much. You need to figure out how are you going to attach parts together. So this violin has nuts and bolts, and they have done a couple of different techniques here. PLA wouldn't work for vacuum forming. If you tried it for vacuum forming, I would certainly use many walls and many top layers and a pretty dense infill, just for the, first of all, it can't deform, or else your vacuum form will be deformed also. So you don't want it to deform under the heat or the pressure. There's actually a decent amount of pressure with vacuum form parts that the form has to undergo. So I would use several walls, maybe 4 walls, and a higher infill, maybe in the, I don't know, 30-35% range, something like that, because it does have to hold up. But I have vacuum formed with PETG before, and it worked okay. I haven't vacuum formed recently with PLA. I did try one time, and the mold cracked, but I didn't do it with that many walls. when you're that was answering a question on the chat. So let's talk a little bit about how you might attach things together here. So they've got a couple of different methods here. One, they've just built some holes, hexes, that you can drop a hex nut. You might can, I don't know if I can ever get it lined up to where you can, yeah, it's down in there. Let's see, kind of like that. It's down in that hole. And so you can just drop the nut in there and then screw a machine screw from the other side, and it's going to pull these together. They've also used this kind of process where, let's get a nut out. These are M4 size, so not that that matters, but that's just what size these are. So you put the nut in here, which is going to be hard for me to do and hold all this stuff. Let's see. I haven't cleaned this hole out either yet, so it's not going to be quite the right size. So you push the nut in there, and then there's going to be another part that bolts underneath here, and then you can bolt through here. So this one, it's sort of captured in the sense that the nut is placed later. You can do this same thing. This Violin doesn't have it. Let's go to TinkerCad and I'll show you. Where did I put TinkerCad? Here it is. So you can build a part, and let's see, TinkerCad has a polygon that's way too big for, let's see, the M4 is across the flats, it's I think 7 millimeters, and across the points I think I had it at 8 millimeters, something like that. So this is a hole that's a little bit bigger than the M4 nut, and so you can put this in, cut this part into here. So let's just join those, select everything, join them together, and there's the hole. And you can print up to this far and do that same thing that we did with the filament change. So make the printer pause, basically. So insert some G-code or click the button in Cura that says pause at layer. So you find this layer, and then drop the nut in the cavity here, and then continue printing with you know, the part on top of this. You don't actually make them in two different parts, but I just needed to show you the hole inside there. So here's our block, and then we would also need, obviously, to put a hole for the screw to go in. I don't know the right size. We'll just pretend. Let's do something like that. Should be round. Well, all right, so we can fiddle with it all day to get it lined up right. In a modeling package, you would just do this, right? So you wouldn't have to worry about this particular part of it. I also don't want it to, I've already cut that hole out, so here we go. Let's just put them together. So now I didn't line everything up, but that's fine. That's not the point. So now you print this bottom part until it gets to the top of where that captured nut, the hex nut, is going to go. You leave it on the printer, cause the printer to pause. You physically go and drop the nut into the hole. At that point, you know, you're halfway through this print or whatever, and then you print over the top of it. And embedded inside your print is that nut. Now that's kind of nice in that it's all the hardware is in there. The one downside, or I don't know if it's the one downside, but a downside to this is that if that nut ever breaks free, let's see if I can get this part off of here again. So if it ever breaks free, you know, it rounds out the holes here that's holding it in place, then there's nothing really you can do about it because it's built inside this part you've printed. So that's why you do see this same idea a lot, but it's more like this where I can actually get to the nut if I need to take it apart. There's another way you can do this that uses these things. So these are heated nut inserts or heated inserts or whatever you want to call them, threaded inserts. They have actual machine, you know, these are brass. They have actual machine threads inside here and these little ridges around them. So what you do with these is you create a hole, you know, the right size hole in your part, maybe like this, or can't hit the keys. So there's a hole. Oh, there's a hole. Create the right size hole, slightly smaller than the diameter of this thing, right? So you want to have a little bit of thing for this to bite into. And these don't just press in. You actually use a tool like a soldering iron, but you can use a soldering iron, in fact. And you insert them, you heat them up and push them into that hole. I don't have these. This violin doesn't use any of those, but you push them into the hole, and they heat up. And as they cool down, they are set there. They're heat set into the part, and now you have actual metal threads in the part. They're pretty cheap. You can get them in a variety of sizes and shapes and lengths and thread types. So if you want actual metal threads in your part, you can use those. Again, they have a little bit of the same issue that the hex nut has, in that if they ever break loose, they're just stuck there. You know, it's hard to replace them, depending on where they are in your design, I guess. But that way, you do get heated, or you do get actual metal threads in the part. Oh, there's a question about PLA and PLA Plus. I don't actually know. I haven't used PLA Plus that much. I know that every day there are more and more materials that have this additive and that additive to make them perform better and better. So I do know that MakerBot has a tough PLA that is probably similar to PLA Plus, and that they do have a little bit higher glass transition temperature. So when you're thinking about a part that needs to withstand heat, it's not the printing temperature you're interested in. You want to look at its glass transition temperature. So that's the temperature for a polymer where it begins to soften. So it begins to come from a solid, you know, the crystal, well, it's a polymer, so I guess it's not crystals, but where the polymer chains begin to soften and it's deformable. So that's the thing that you're interested in when it comes to, is this part that I'm printing gonna survive being on the dash of my car in the summer, or something like that. Look at the glass transition temperature of it, not the printing temperature. Obviously, if you get to the printing temperature, you know, then it's just gonna become goo, so that's not gonna be good. But much lower than the printing temperature is called the glass transition temperature. So if you can find that piece of information, that'll tell you if the part is going to, or the material is going to be able to withstand the heat that you expect it to have to deal with. And I don't know what the glass, I don't know if PLA Plus changes the glass transition temperature or if it just makes the part tougher, because I don't really know what they've done to the PLA to make it plus. So I just don't know. Let's see. So here are some guidelines for things to think about when you're designing for printing. Holes in the part. So particularly like whoops, covered up. Like this hole goes all the way through this piece here, and then through the other piece that's going to go on the end, so that a tube or a rod or something, some kind of stiffener, can go through all of that and keep the neck more or less straight when you put the string tension on it. So it's hard probably for you to see in here, but I'll try to make it focus on it. Yeah, it's just not going to. But anyway, I printed this with 4 walls. So, and I printed it standing up. Remember, we had the problem with this piece because I printed it standing up. But I printed it standing up on purpose because I have a lot more confidence that I can draw circles in the XY plane on this printer than if I were to lay it down flat and create that same hole, this same hole, all the way the length of here by stacking layers on top of each other this way. But this way, I'm stacking circles on top of circles, not rectangles to make circles, if that makes sense. And so part orientation of how you're going to print the thing does matter, particularly for features that need to maintain a certain size, like the diameter of this hole. I also printed it with 4 walls because it's going to need to have enough strength to actually do it. If I just put 1 wall in there and that wall is surrounded by the coarse infill, then it's going to be really easy for that infill to crush all around it. So if you're printing holes and bosses and features that need to have some strength to them, instead of just printing the thing solid, just print with more walls. And usually 4 walls is a good number of walls that you've gotten most of the strength out of it without making it just completely solid. And then your infill can be 20% or something like that. You can, if you need to, print completely solid. There was something I was printing the other day that I just made completely solid. I don't remember what it is now. Oh, the flute. The flute. I made it completely solid because I didn't want any air trapped inside or I wanted minimal air trapped inside the walls of the flute. And the ocarina, I guess I never showed you the ocarina. I printed it completely solid. But as far as function goes, making a part that can withstand some kind of stress, try to do a couple of more walls than you would normally do. 4 is good. Try to orient the part so that the features that need to maintain their shape, circles in particular are bad about this, are printed parallel to your axis. At least on this printer. Other printers, they might have some different motion, but most printers, like the consumer level printers, the X and Y direction is going to be a better plane to print circles and squares that need to remain square and things like that. Let's see. We talked about using the horizontal expansion. If you don't really know ahead of time, so this is something you have to calibrate for. If you need to print this way and you need to print circles and holes and everything going into the part, then it can be that the holes just they're always undersized or they're always oversized. Now, it is much better for them to be undersized with 4 walls, and you can come back and ream them to the specific shape you need. So reaming is sort of like drilling, but it's a particular tool called a ream that is a precision device for making an exactly sized hole. Probably overkill for 3D printed parts, but if it's necessary, then you can do that. So it's better that they're undersized so that you can always remove material later in some kind of machining process. But if you need to adjust that and you don't want to go into changing the number of steps per millimeter for your X and Y axis, we did that for the extruder, the E steps, but those kind of steps exist for X and Y and Z also. And you don't want to do that, then in most slicers there is that horizontal expansion that is a percent. Well, I think some it's a percent, some it's an actual number, like a millimeter number. And you can make things bigger in general or smaller in general. For the whole print, I talked about it on just the first layer, but there is a setting for the entire print. Let's see if I can find it. Here's Cura. We have errors. So horizontal. And then there it is right there, horizontal expansion. I think in Cura here, this is actually millimeters. So it's how many millimeters, and it's usually, fractions of millimeters. Do I want to make some parts bigger or smaller? And so it even gives you a little call out here that positive means it's actually going to make the holes smaller, and negative will make holes larger. Because it's of the way it's thinking of positive and negative. So it's not necessarily thinking of the diameter of the hole. That's why they explain it right here. And then there's the one for the initial layer. And if your other part shapes are fine, it's just the holes, the voids on the inside, there is one that's just for the holes. So this one's for the entire layer. or the entire model. This one's for the first layer, and this one's just for holes. And they don't have to be round holes. It's just any hole on the inside of the part. So those 3 settings. You would print basically a flat sheet with a bunch of shapes inside of it and measure those shapes. Maybe I'll make one of those up shortly. Not today, but I'm sure there's some that exist. But you make these to create holes of a certain size, and then you measure them after they've printed, and you adjust the expansions numbers here so that you can create the exact dimension you want. If you don't want to go in and try to tune your printer itself to create the right size holes. All right, so let's see. What else might we do? Walls, I talked about that. If you're using fasteners, you're better off using 4 walls. If you're not using fasteners like nuts and bolts that have to go into holes and things like that, then 2 walls are probably fine. But in general, the easiest way to gain strength on your part that you're printing is just to go up to 4 walls. And you can also increase the top and bottom layer a little bit. I think the default is usually at 3. And you can create, maybe 4 top and bottom layers. Another thing to think about, though, when you're thinking about the walls, is when you build the part, to begin with, try to anticipate that I'm going to print this part on a printer that has a nozzle in it, and that nozzle diameter that I'm using, the nozzle for the diameter of the little hole in the end, is whatever it is. So 0.4 millimeters is kind of the standard, but there are others. You can order, and probably around here somewhere I have a whole set of different diameter, so different nozzle diameters, nozzles. There are reasons you might want to go into larger or smaller. Larger nozzle diameter, obviously you can print faster because you can squirt out more material. Smaller, you're going to print slower, but now the little stream of molten plastic that's coming out of the nozzle is thinner, and so you can get higher detail out of that. So you could change a fundamental thing about your printer pretty easily just by changing out the nozzle. If you do go to change the nozzle, there are a couple of things to be aware of. One of them is that don't just go, like my printer's sitting here cold, don't just go cold and try to unscrew this thing, because there's a really good chance for that brass nozzle has seized in the block that it's in. It's in an aluminum block usually, the heater block itself. And there's a really good chance that you will shear the threads, or you just shear the entire nozzle in half, and then you've got to figure out a new hot end. So heat it up. It doesn't have to be all the way to printing temperature, but heat it up and then unscrew it. Otherwise, and when you're doing this, I don't know if I can get a good position where you can see this or not. Let's see if we can. I don't know if we're going to be able to see down in there, but let's see. Let's see if we can see. Maybe, sort of. Well, so this one, again, it has the little silicone pad around it, but when you're unscrewing the nozzle, get you a tool, pliers, a wrench, whatever, and hold the block also. If you don't, then maybe you don't break the nozzle, but you break the heat break. So there's a little thin tube that connects the colder side of the hot end to the hot side of it, and that's called the heat break. We'll look at all these parts later on when we take it all apart, but try to hold the block and unscrew the nozzle after you've heated it up, and then reverse all of that to put it back together. Actually, when you put it back together, heat it up and turn it maybe a quarter or turn to really seat it in there. If you try to reassemble it cold, you can reassemble it cold, but don't leave it that way. Heat it back up and make an extra quarter turn or so. Otherwise, the filament's going to leak out past the threads. It's not going to seat in there very well. So we'll take this all apart later so you can see all the pieces, and I'll go over that again. But don't just think you can unscrew the nozzle and screw it back in and everything's going to be fine. If you just do it that without a little bit of knowing what you're doing there, there's a good chance you're going to break parts in here, or you're going to get it back together and it's going to leak everywhere. So just make sure you know what you're doing when you go to change out nozzles, if you do that. All of that to say, these things come in different diameters. So when you're designing your part, make sure that you design it with features that fit that diameter of nozzle. So if you know you're going to print it on a printer that has a 0.4 millimeter nozzle, don't make walls that are 0.6 millimeters, because what's it going to print? It's going to print one wall, and then it's got 0.2 millimeters that it couldn't figure out how to print. So there is the print thin wall feature in Cura, so it'll do something, but it's probably not going to be able to produce a 0.6 millimeter wall if you have a 0.4 millimeter nozzle. So make that wall 0.8 millimeters in your design if you really need something that thin, but make it 0.8 so that it can print two 0.4 millimeter walls side by side. And so for all of your features in there, always in the back of your mind, think about, is this going to work out when I slice the thing? Am I building things in increments of whatever layer I'm going to print this at? So I'm printing at 0.2 millimeter layers. So I need to make things that are tall. Their height needs to be an increment of 0.2 millimeters if that's this layer height I'm going to use. And walls and features need to be increments of 0.4 millimeters thick, so that when it goes to slice it and print it with my 0.4 millimeter nozzle, it prints entire, integer number of walls. It doesn't try to print half numbers or fractions of numbers. On thin walls, so if you do need to print a part, I don't have a real good example, but maybe here, full of stuff, full of junk. But if you do need to print a thin wall here, then there's a decent chance when you print this that thin walls like this want to peel up at the corners. So these corners want to peel up. And if your printer has difficulty sticking down to the bed, then there are a couple of things you can do. These thin walls, a lot of times they want to warp, they want to peel up. You can add, this one doesn't add it, but you can add, what it kind of does, you can add thickness to them. You can kind of see there's a little bit of thicker part. You can add ribs in there. These are all kind of the same type of things that if you were designing this part to be injection molded, it's the same type of things that you would think about, because it's a similar process. You're melting material and then extruding it or injecting it, and then it's got to cool, and it's that cooling part that most plastics, as they cool, are going to try or they're going to want to warp. So you can add features. Maybe if you know that this corner is really bad about warping on your prints, build a little feature into the base down here that you're going to erase later. You want to cut it off or trim it off later after it's printed. But the whole point of that feature is to hold that corner down. So I'm thinking of something just like a circle around here. In fact, some slicers have that. I don't know if Cura still does or not. Let's see, I'm looking at, I don't see right now. It used to be that Cura had some little helper blobs, like they were just little disc that you could add to corners inside Cura. I don't see that right now in here, but maybe it's still there somewhere. I'd have to look it up. But if you know that that's going to be an issue on your part, build them in from the beginning. If you know you're going to need support material, so like this is I didn't want to print this with support, and so these little overhangs here, they're kind of jaggedy. So either build in the supports to the part as part of the design, or make sure that your angles here, instead of, I'll draw the picture here. So let's see, which way is the right side up? That way. So instead of, this is the front view, I guess. So this is the bed down here. Instead of building it like this, where it has to have the support material all in here, if you can, just build it like this. So that now in each printer, it's going to have a different angle right here that it's capable of doing. In general, if you're unsure, in general, a safe angle is 45 degrees. But some printers can print angle, overhangs at 60 degrees. Well, this angle would be more like 30 degrees or 20 degrees even. Obviously, this one, when it goes to print this layer here, there's nothing to support it at all. But a safe angle here is 45 degrees. And if you've done the test on your printer to see what your printer is capable of, then you may be able to make this, more shallow. You probably won't ever get it to make, completely horizontal, except that if you need completely horizontal, you can go in, build in a little sacrificial piece over here, and when the printer gets to this level, it will bridge across here. And so your printer can print in mid-air as long as it has a start point to start from and it has an end point to land on. It can actually bridge across there. When you're printing the benchy, the little cabin is one place to look to see how well your printer bridges, because it's got the square window in the front of it, I guess it is. And across the top of that, it has to bridge from one post on the left to the post on the right side, and it's doing the same kind of thing here. So that's the thing on your benchy you can look at. If you've gotten one printed, you can look at it and see, is it making a good bridge here? If it's not making a good bridge, it'll be something like, you'll have layers that kind of droop here when it goes to print them. And so if you have these drooping layers, then that's maybe a cooling issue. And there are bridge settings in your slicer, like how fast does it go across there and that sort of thing. But generally, is your printer, the layer cooling fan, is it cooling this material fast enough so that it more or less solidifies in place as it gets across there? So those are some things to think about as you're designing this part, is these overhangs and what your printer is capable of doing. General design principles still apply, like fillets. Anytime you have a corner, like this actually does have a fillet in it. So you can see right here, there's a fillet on here. Now, if I didn't need this to be a sharp corner, I would have actually filleted the outside, not because it needs a stress reduction there. Fillets are generally used to reduce stress, right? But because that as this printer's coming around, instead of making a hard turn, one axis has to completely stop and another axis has to start moving, it transitions. And so if you can make these smoother transitions, you'll get smoother prints in the end. If I have to stop and go in another direction, you're going to get a little shaking in your print, and you'll get some waves in the wall of the print. So if you don't have to do that, then design it with curves so that you're telling the printer, hey, make a transition here, don't stop and then move in another direction. In general, on the if you're using a fillet radius to reduce a stress concentration somewhere, so like this little angle right here, this sharp angle would be a really high stress concentration. So in general, the radius here needs to equal this wall thickness. So whatever that is would be the radius of that fillet. It's getting all cluttery there, but that's just a general guideline. We talked about bridging. Obviously, you got to get the part to stick. We talked about elephant's foot. I don't know if I drew a picture of, and maybe you didn't understand, but when I was talking about this part, and I was talking about the elephant's foot down here, what I mean is, I've got this shape. I want it to be kind of like this, right? Oh, well, I didn't make those line up. We'll make it a new part. I want it like this, but what actually happens is when I'm printing this first layer, it's squishing it out bigger, and so that first layer or two end up thicker than what I wanted. So that this part over here and this part over here are outside of the dimensions that I actually intended for it to be. That's the elephant's foot. And we talked about you could cure that by raising your z-axis a little bit. You could build this part this way. So you just put a chamfer. Oh, I've got too much stuff in the way now. Chamfer in your part itself so that when it got squished, it basically squished it back out to the size you wanted it to be. So when it prints it and squishes it, it's like this now. And it's the size you want it. You can file it off later. There's a lot of different ways you can deal with it. You can do the horizontal expansion to shrink that first layer in. Or you can do the initial layer horizontal expansion to shrink the layer in. You wouldn't necessarily want to shrink the whole part. With this, if you have lots of spires, so little peaks like this, obviously retraction is going to be an issue there. This one is intentionally set wrong, but if you have a part that, like the benchy, so the little smokestack on the top of the benchy is good for measuring how well your cooling is working. So if you just can't get it to work, what you can do is, when you're building the part, so here's the part you want. You want this one, and it's going to have this relatively thin, tall structure, and it's going to be hard to cool this because it's just these little short layers. It doesn't take very long to print them, and so it stacks hot filament on top of still hot filament that it printed previously. And so it's going to be kind of warped sometimes if you don't have good cooling on this part. So some things you can do, you can try to improve your cooling. I printed, I think I showed on Discord, I printed a little cooling duct to add to mine to replace, I don't know what I even did with the old one. Here it is. Here's the old one. And I printed one off of Thingiverse for the Ender 3 that directs the cooling from that layer fan more directly onto the part, so that you can try that. Another thing, if you just can't make it work, is just go over here to the side of your part and print something that you don't need. Print another one of these, maybe you need 2 of them, or print something that's just a sacrifice, so that what happens is as your printer is printing, it prints over here, and then it has to go all the way over here and print something. That lets this have enough time to dry, or not dry, but cool down, so that by the time the printer gets back over here to print on top of it, the next layer, this layer is more solid. It's not still molten. And so making the print head move away, do something else for a while, gives this time to actually cool down. So sometimes printing 2 of the same parts will actually help when you're trying to print these skinnier pieces that are going to have really short layer times when they go to print. In Cura, there is a minimum layer time setting. Let's see if I can find it. I think it's just called minimum layer time. Oop, that's not Cura. There's Cura. Let's see. Minimum. There it is, in cooling, minimum layer time. So mine is set to 10 seconds, although I don't think it ever actually takes 10 seconds to print. Well, the minimum speed, I guess, is also, these two probably work together. So it will only slow down to 10 millimeters per second, but that might override the fact that it takes 10 seconds to print this layer. So you can mess with these two also to get a similar effect, where the goal is to let the previous layer cool before you put new filament on top of that for PLA. Let's see, what else can you do? You might be getting close to the end of all the things I was thinking of. Yeah, we talked about that. Oh, well, yeah, here's some obvious things that maybe you don't even think about. You get to thinking that, hey, I'm going to print this part, and it's going to be great. I'm just going to hit print on the printer, and it's fine. And that's one way to look at it, but don't be locked into that every feature of your part has to be printed. If you need a really long piece like this, maybe it's better not to print that, but to print a hole to receive a dowel or something, a styrene dowel or a wooden dowel that's that shape. For one thing, printed really thin pieces like this are really going to break easily, just because there's not a lot of layer surface area between the layers to hold them together. So don't get locked into thinking that everything has to be 3D printed. Don't forget that you can take other materials. Maybe this needs to be a steel rod, and instead of printing the tower here, you print a hole to put the steel rod in that takes the place of the tower. Use fasteners. So you've got all kinds of, nuts and bolts and screws and washers that you can use to hold things together. Don't think you have to print the entire thing as one part, but you can have an assembly. That's also better. If I were trying to print this, first of all, I'd have to have a really big printer to fit it all in there. But what if this happened again? Instead of, this piece by itself was 12 hours of printing time. So if I do have to reprint it, that's only 12 hours. But if it's the entire thing as one big print, then how long do I have to print a new one of those? So it is nice to be able to assemble it and just redo the parts you need to redo versus the whole thing going bad. And I already mentioned it, but do think about printing orientation for strength and for the features you're trying to preserve. Like these holes, you can actually see, I think you can tell, they're not perfectly round. This part, you can see the layers. This part was printed on its end, and these holes, this is where the tuning pegs are going to go. They're not perfect circles. They're a little bit oblong because instead of printing circles, it printed a bunch of rectangles on top of each other to create something that looks like a circle. So if this mattered, now there's enough slop in these that I'll be able to put the tuning pegs in here. But if this mattered that it was a perfect circle, like this hole down here does matter, then this would not have been a good orientation to print these. So there's a lot of different little things to think about when you're trying to print something for the purpose that you're going to print the thing. You're going to design it for the purpose of printing it. Think about the strength of the layers. These parts, the layers are stacked on top of each other here. So it's really strong in compression this way because I'm just trying to push layers together. It's kind of weak in shear though. So the layers themselves are easier anyway to debond. And so this part will not be as strong in shear or bending. So bending has a shear component to it and a tension and a compression component. So it's not going to be as strong in there. That's also part of why it has this truss rod through the middle of it to reinforce all of that. Now that happens on an actual violin also. Well, I don't know if it happens on a violin. It happens on guitars. I assume violins have a similar thing to stiffen the neck also. But think about the strength of the orientation of the layers that you're going to print. Are they going to be strong in the direction that the force is going to be applied when you actually put this thing in service? I think that's a good overview. I was going to go into TinkerCad. We did go into TinkerCad a little bit. I was going to go in and show some more things there, but I think we'll save that. I'll jump over to Zoom in case anybody has some last minute questions. This is, until January, whatever, 3rd, 4th, something like that. We won't actually be back. If I do post anything, they'll be just optional. Maybe I paint this guy and show you some details about how to do that, or maybe I come back and show this thing in action. I fix the cam for it. But those won't be things that you have to go and watch if you're part of the class. It's just I posted another video. You can watch it if you want to. The next one will actually be over in, what day is it? Let's see. Oh, I didn't put the days on here. Well, it'll be after the new year, and we'll get back on topic then. I'll try and grade any benches that you've uploaded or any assignments you've uploaded. I'll try and grade them sometime over the break so you kind of have an idea of where you're at on those. But until then, I'll go over to Zoom if anybody needs any questions answered, and then I will see you guys at least sometime in January.